All right, so moving on. This is a slide that I like to show when I talk about my nanotechnology work. It's called The Scale of Things, and it's from the Department of Department of Energy. And it shows, let's say, things natural on the left side, things man-made on the right side, and this scale that you can't read down the middle shows, how big these things are. So like the head of a pin, millimeters, that corresponds to millimeters. And you go down and down, and you get to things like red blood cells here, 7 or 8 microns. And you get down here, here's DNA, the diameter of DNA, which is in the nanometer range. Well, that's the world that I usually work in. So now let's transition to the world of the oil spill. So we got to zoom way out in order to put it on the scale, or else, I'd have to point it out way up here. So on this same scale, where the oil spill comes in is at the meter length scale. You've all seen these pictures on TV, and you look at the flow coming out of the riser pipe, and it looks bad, it's disturbing, but you don't really have a sense of the scale. So the scale, this is a picture from June 3rd, and that was the time frame when the riser pipe, which the blowout preventer was right about here, the riser pipe had been sticking out here and then was kind of kinked off to the side. And on June 3rd, what they did was they came in and they cut it off. And now you see this fountain of oil shooting out. And the length scale here, the diameter of the pipe where the jet comes out, it's nearly 2 feet across. So the flow that's coming out of this thing's coming out of a hole that's that big around. And, you just, to appreciate the scale, imagine, the flow's coming out from something this big around at a couple of feet a second, actually at about a foot a second. So you get a chunk of oil that measures this big every second, right? And there's 60 times 60 times 24 seconds in a day, so that adds up in a hurry. All right, moving on. So this was the first video that BP released on May 12th. The video was shot the day before by an ROV that was on site. And what you see here, I think this video was widely watched. You see what's called the riser pipe here, and this is the 2-foot diameter pipe. So right here is about the diameter, that 2-foot diameter pipe. And what you see coming out, the black stuff is oil, but there's a little bit of dissolved gas, methane gas in it. And then the lighter colored material, is methane gas that's already separated from the oil. The environmental impact of that methane is not well known. I mean, it's a greenhouse gas, but it's less severe of a greenhouse gas than CO2. And the volume that's being emitted here isn't enough to make a dent in the U.S. emissions of CO2. But what isn't known about the methane is what effect it has on the marine biology. So the methane, this is a mile under the sea surface. So as the methane bubbles up to the surface, most of it doesn't make it to the surface. Most of it dissolves in the seawater. And when it dissolves in the seawater, there are bacteria that like to eat it. It's a very energetic food. And when they eat it, they metabolize oxygen as well. So essentially, they suck all the oxygen out of the water. So right now, I'm not sure, and I think nobody's sure what the environmental impact is of that methane. But nobody's really worried about it because it doesn't wash up on the beach. But this is another important issue to think about, maybe to ask people about if you have the opportunity. So anyhow, and my primary concern was what's going on with the oil. All right, so this video, as I said, was released on May 12th. And on May 12th, on May 13th, Richard Harris from National Public Radio, here's Richard Harris. He's on the short list of people that my wife hates now. Richard Harris sent me this email, and he says, Dr. Worley, I'm trying to find people who can calculate a flow rate from this movie. And he says, I understand PIV is the perfect tool. Since you literally wrote the book about it, I'm coming to you. Could you estimate the flow depicted in the video, given that the pipe diameter is 21 inches? Please call when you can. So I'm a National Public Radio listener, and I thought, oh, cool, Richard Harris is emailing me. So immediately I went to YouTube and I took a look at that video, and I thought, yeah, well, when I watch it with my eyes, just cursorily, just at a surface look, I can see turbulent structures. I'll show you some more. I'll show you exactly what I'm talking about in a minute. I can see the, let's say, bumps and variegations of this jet of oil as it shoots into the sea. Well, that's not exactly particles, right? Particle image velocimetry tracks particles. So these aren't particles, they're turbulent structures, but nonetheless, there's something that's moving at roughly the speed of the flow. And so by tracking those turbulent structures, I can estimate the speed of the flow. So I gave Richard a call back. Unfortunately, I didn't send an email because I wish I had a record of it, but I gave him a call back and said, yes, I can do this. And then he started feeding me information, got me this video, got me a high-resolution version of this video, and I did the calculations on the flow rate. So I thought I would show you guys just how easy this is. So, BP's on the record as saying this flow can't be measured. In fact, at about this time frame, BP's on the record saying this flow can't be measured, not by us, not by anybody. And, well, words like that have a way of coming back to haunt you. And so I said, yeah, actually I can measure that. And two others as well. So I wasn't the only guy who measured this, but Tim Crone at Lamont Doherty Labs, which is affiliated with Columbia, and Eugene Chang at Cal Berkeley also came up with numbers, and we were all in the same ballpark. So I thought I'd show you guys just how easy this is. It's dead simple. All right, so although unfortunately the people in back may have to download this later or something, but I've got a little black and white picture of the video that we took a look at a minute ago. Yeah, actually, I think everybody's going to have to imagine that they can see this. You see the arrow there. I think everybody can see the arrow. You're going to have to trust me. The arrow is pointed at one of these turbulent structures. It's a little, essentially it's a little lump on the side of the jet, and that little lump starts out where I've pointed here and moves to where I'm indicating there. So you can't see the structure, but you can see the arrow move back and forth. And so by simply putting my cursor on that turbulent structure, reading the address, the XY coordinates of it at time 1, reading the XY coordinates of it at time 2, I can calculate how far that structure's moved. That structure in and of itself, that one structure, came out to within 10% of the numbers that I got when I ran my PIV code. So, I mean, not only is it calculatable, not only is it doable, it's just dead easy. Oh, I didn't say that on network TV, but anyhow, it's just not that hard. So, so this is the low-tech version of it, and I calculated, because it moves in the X and Y direction, I did a little trigonometry, calculated the displacement is 11 pixels, 11.7 pixels between image 1 and image 2. Now, I know how far it's moved in pixels, but I need to know how far it moves in real space. I need some kind of length scale. So over here is this pipe, and we know that the pipe diameter is 21.5 inches outer diameter. And so if I measure from the top to the bottom of the pipe, that's so many pixels. It happens to be a couple hundred pixels. I know that equals 21.5 inches. So right there is a correspondence from image space to real space. And at that point, it's all downhill. I mean, it's just multiplication to figure it out from there.